thank. Okay, so I'm here. I'm introducing Mads Brandbyge. And so he's professor at the Technical University of Denmark at the Department of Physics and at the Center of Excellence for Nanostructured Graphene. So he has obtained his PhD in physics from DTU in '97, and he's done a postdoc at the University of Tokyo, and after that at the Microelectronics Center at the DTU. So he was promoted to associate professor in 2004 and full professor in 2015. His research interests are focused on theory of transport properties of nanostructures with focus on electron and heat transport, electron-phonon interaction, and current-induced effect. And his group has developed now widely used methods and softwares. And well, I guess now we all want to listen to him. And again, Mads, thank you very much for giving this seminar. And yeah, by the way, sorry, one more thing. Mads is fine with questions asked during the talk, so feel free to raise your hand and ask questions. Okay, thank you, please.
Okay, thank you very much, Marco, for this nice opportunity. So yeah, so I'm going to talk about the simulations we're doing on novel 2D materials. And just to get started, I want to show where I'm from. So I'm from Denmark, this small country here below Sweden. And the Technical University, that's a little north of Copenhagen, the capital here on this island here. And it's located in a quite nice green area. And you can see the sea here, and you can see Sweden on the other side. So quite close to Sweden. And this is our campus. It's nice and green. And we have some very nice facilities for research in nanostructures. So we have a big clean room, and especially in our department, we have a 2D materials lab where we are growing 2D materials and making devices and characterizing these. And we also have a nice microscopy center. So just to give a few numbers, the university is pretty old. It was founded by Hans Christian Ørsted, the discoverer of electromagnetism some couple of hundred years ago. And it's somewhat smaller than Nanyang with 11,000 students. We are in this nice alliance with the European universities, technical universities, but also technical universities or technical institutions in Asia, and in particular Nanyang. So I'm looking very much forward to a nice collaboration with Marco in the future. So the physics department, oh sorry, it's bad spelling, is focused on applied physics. So it's not like cosmology or high energy physics. And I am in the section for nanoscale materials and devices. So that was just a small introduction to where I'm from. So now let me go to the motivation of what we're doing. And I think for what we're doing in my group, there are like two promising trends which motivate us. And one is that now 2D materials, they can be grown in many different varieties. There are maybe more than several thousands of these materials, and they can also be exfoliated and stacked in various ways. So there are a lot of techniques now evolving for making devices out of these materials. And for instance, there are also techniques for how to connect these two metals, for instance, by etching through stacks of these materials and putting metals on the edge here. And the first principle calculations play an important role in this development. And for instance, in our department, there's this computational database with, let's say, computational predictions for novel materials, but also band structures and properties for a lot of 2D materials, more than thousands of these. So this is one trend. The other trend, that's bottom-up organic networks. For years, people have been able to make precursor molecules and put these precursor molecules on metal surfaces and then grow various shapes of nano ribbons. Let me just check if I can show my pointer here. Do you see the mouse?
Yes, we can see the mouse.
Okay, then I'll keep with the mouse. Okay, so you can grow all various shapes of nano ribbons, and that's a very nice development for years. But more recently, it has been shown to be possible to actually create 2D materials based on carbon. So, for instance, this is called nanoporous graphene, and it's basically nano ribbons, but connected by strong covalent bridges. And the main interest of this is that now you can actually not only look at these materials on a metal surface, but you can actually exfoliate it and put it into a device and make devices out of these. So this brings some interesting questions for theory and simulation, because we like to know from theory and simulation what new types of devices could we imagine making out of these materials, and what kind of design rules can we apply to these devices. And of course, this poses a lot of challenges. First off, we want to be predictive. We want to be able, without any fitting parameters, to model devices. And since it's devices, we want to look at working conditions. So we want to apply electrostatic gates, and we want to look at what happens when we actually apply a bias and have a current and non-equilibrium in the system. And then a third challenge is, of course, the device size, because now when you look at devices, then it's not just a few atoms in a unit cell, it's maybe structures up to 100 nanometers. So there's quite a few challenges here we are facing. So this is the outline of the talk. I will just briefly mention the computational main tool we are using, which is a combination of density functional theory and non-equilibrium Green's functions. And then I will spend most of the time just showing different examples where we're using this method and what we learn from the method. But let me just go through the ingredients in the calculation. And the first ingredient, that is that we are treating the system as an open quantum system. So we are not using periodic boundary conditions, but we are looking at a computational box containing some structure, and then parts of that structure is actually attached to semi-infinite electrodes or reservoirs of electrons, and it can exchange particles with these reservoirs. So the other ingredient is that when we want to do electronic devices, we have to be able to include the electrostatic environment. So we can apply, for instance, electrostatic gates to various parts of the system, and this way induce charges in the structure, or change the Fermi level, if you would. And the third and maybe most important, most interesting to me thing is that we want to look at the non-equilibrium situation. So we are able to apply a finite bias to between our electrodes, so we can have different chemical potentials in different parts of the system. And this has been implemented for many years now, and we're keeping developing this. And it's basically, as I said, this merger of density functional theory, where we are using codes with pseudopotentials typically, and we're also using atomic centered basis sets. So to some extent, this looks like tight binding. It's just a complicated tight binding model. And then we have merged this with non-equilibrium Green's functions. And with these Green's functions, we can take into account in an exact way the coupling to these semi-infinite electrodes or reservoirs. And this is done using the so-called Selfenergies. So in this way, we can calculate the electron density once we are applying voltage between the reservoirs. And since it's a Green's function method, it's also possible in a sort of a systematic way to include many body interactions in this computational region, the central region we have in the device. But I'm not going to talk so much about this part. And this has been implemented in our freely available Trans-Siesta code, and it's also implemented in a commercial code we use, which is called Quantum ATK and marketed by the Synopsys company. So I just mentioned 2 electrodes, but actually in our Trans-Siesta method, we can actually include any number of electrodes. So we could look, for instance, as a T-junction between graphene and calculate what is the conductance between the different arms here. So it just shows that it's quite flexible in that sense also. But now let me start by showing an example where we get a non-trivial result out of this non-equilibrium. So here I just look at a small graphene nano ribbon between graphene electrodes, and we apply a bias between the top and the bottom here of 0.5 volts. And here you see the voltage drop. So that is the change in potential for the electrons. And you see that it's like a ramp, which you might expect. But then we also apply a gate. In this case, the gate is 0, so there's no charge on the gate. But we apply charges on a gate such that we can induce carriers, extra carriers in the system. So if we induce extra electrons in the system, so do N-doping, then you see this interesting thing that rather than having just a linear ramp between the 2 electrodes, the main voltage drop is moved here to the high potential electrode. And on the other hand, if we remove electrons, so we have p-doping induced by the gate, then the voltage drop moves to the other electrode. So it shows that this voltage drop in the device can be manipulated by the gating. It's not that I know a concrete application of this. It just shows that, you know, from the beginning, once you have non-equilibrium, it's not clear exactly what kind of potential landscape you will have. So you have to do the calculation in the device to get that. And we can take, of course, the calculation apart and see what is the reason for this change in voltage drop. And that's basically the change in charge in the ribbon part here. It will be, it will change its charge once we apply the bias. And we can understand this change in charge by looking at basically the density of states in the electrodes. But this is just to show sort of the way we operate. We do these calculations and then we analyze the results afterwards to understand more deeply what goes on. Now let me skip to something which is more related to experiments, and that is the contact between metals and graphene. Because of course we need to contact the 2-dimensional materials. And one way is to use graphene as the electrode, but of course then the graphene have to be contacted. So we in the first place want to be able to control the contacts between metals and graphene. And years back it was shown how you can actually make 1-dimensional contacts to graphene if it's sitting inside a stack, let's say of hexagonal boron nitride, to isolate it, to encapsulate it. You can actually etch through this stack and then apply metals just on the side and have like a 1-dimensional metal graphene contact. So in the experiments, it's known that the resistance here changes by orders of magnitude when you vary the metal and also when you vary the processing steps. So we try to do calculations to figure out what goes on. If you just do a calculation of a completely ideal graphene metal contact at the bonding distance, the relaxed bonding distance between graphene and metals, you see basically that the different metals from nickel here to gold, they have roughly the same resistance within the same order of magnitude, maybe a factor of 2 or 3 or something. So it will not be an ideal contact. So the question is, what happens, for instance, if you have some residues from the etching process, and this will typically be oxygen or fluorine sitting in the contact between the metal and the graphene. And if we put that into our calculation, then we see that now the different metals, they vary by maybe an order of magnitude or two. So this is more in line with the experiments. So we guess that we will not have this perfect contact. We will have oxygen or fluorine sitting there, but we're not sort of have all the variation you see in the experiments. But of course, then you can imagine that this is not just a perfect contact, but you will have some roughness. So you will not have ideal distances, but somewhat unideal distances. And then you get a much bigger variation, say 2 or 3 orders of magnitude, which is more like what you have in the experiment. So we guess that both the passivation, but also the fact that you have not a straight edge here plays a role. And then from the calculation, we see one more thing, and that is that the metal reactivity probably also matters when you make the contact between the metal and the graphene, because if the graphene is passivated by, let's say, fluorine, then once you take a metal and make contact to the graphene with the fluorine on, then if the metal is reactive like titanium here, the titanium surface, then it's able to strip off the fluorine sitting there and make a cleaner contact and getting a lower resistance. So there are some factors we need to be able to control in order to really optimize these contacts. Now let me switch to a transistor, to an actual device. And here we are considering a graphene MOS2 transistor. So MOS2 is a semiconductor, so that could make a semiconducting channel. And since graphene is a semi-metal, we could use that as electrodes. So here we're looking at a source drain where we are overlaying graphene with the MOS2. And then we could say, okay, we put now, to make it a transistor, we put a gate. It could be like a back gate, or it could be a top gate. And in the first place, you might think that, okay, it doesn't matter if I gate it from the back or from the top. This is the computational setup, just to show you sort of the size of the calculations we are doing. But this is the result. And what it shows here is the source drain current as a function of the gate doping. So the gate charge, we are controlling the charge on the gate. So that's like a gate voltage if you put in the capacity of the gate. And what is striking here is that the current and the transconductance, so the slope here in the current, is very different if you use a back gate and a top gate. So you get a much more responsive transistor if you use the back gate here. And why is that? In order to analyze it, we can look at the electron transmission from source to drain in the transistor. And that's these curves of different colors. And the different colors, that's basically when we turn on the gate charge. And the current is actually due to thermionic emission. So this gray part here, that's actually the voltage window. So that's the bias. But the current is running due to this thermal tail that we have here, and it's going mainly into the conduction band. So it's the conduction bands which conduct in this device. And you can see that when we do the top gating, then the conduction band is just moving slowly towards the voltage window here. So slowly down in this exponential curve here. So not turning on too much, but we have a different behavior when we do the back gate. Here it's moving much more rapidly towards the voltage window, and we turn on the current much more rapidly. So the reason for this is actually, in the end, once we've done all the complicated calculation, pretty simple. It turns out that this device is actually controlled by the Schottky barrier between the graphene electrode and the MOS2. That is the main working principle of this device. So what happens when we gate it is that we shift the conduction bands towards the Fermi level of the device. So it's basically this Schottky barrier here which controls everything. And if we have the gate and the graphene and the MOS2 in this sequence, then the graphene, because it's semi-metallic, is actually screening out the effect of the gate. So it's not shifting down the bands of the MOS2, the conduction bands. But if we have the gate and the MOS2 and the graphene, then the MOS2 is actually sitting sort of in the capacitor between the graphene and the gate. And in this case, we are much more effectively shifting down the conduction bands of the MOS2. So the upshot of this is that when you make stacks where you want to make transistors based on the 2D materials and you use graphene in the stack as the electrode, then the stacking sequence matters. And this is actually a nice thing because it means that the gate is actually only effective from one side in the stack. So we can actually have different stacks with transistors where the gate is only acting for transistors in one direction, which is kind of nice. Let me move on to some materials which are less standard, and these are called Genus materials. And the basic idea is that if you take something like MOS2 and put it on a surface, then you can actually strip in a process the sulfur, replace it with hydrogen, and then in another process step, you can replace the hydrogen by selenide. And then you have made a dichalcodonide 2D material, but it's a Genus material in the sense that one phase here is different from the other phase. And in this sort of illustrates in this two-dimensional material business that, you know, you have standard materials, but you can not only stack these in new ways, you can also take the material and even change that the two phases of the material. So there's a huge number of possibilities. The interesting thing about this Genus is that it's a semiconductor, and it's a direct bandgap semiconductor in this case. But also there's a built-in strong dipole in the layer, because you have a charge transfer from the selenium to the sulfide. So you have a layer, a dipole layer, and it's quite strong. So it means that there's a potential difference between the two sides of this Genus structure of 0.7 volts. So now what can we use this for? And one thing that we started to play around was, if you stack this material, what happens then? So you can imagine that if you stack it, then the dipoles will actually add up. So it means that on one side of the stack, the material would be p-type, and on the other side here, it would be n-type. And of course, you could continue maybe this stacking of p and n-type. You could think that, okay, it becomes more and more p-type and n-type, but of course, it will start to saturate once we hit the bands here. But it means that we could actually have a very strongly doped p-type on one side and a strongly doped n-type on the other side. So now we started to think about what kind of devices can we make out of this. And the first thing which became clear to us is that, okay, if you just put metal contacts on this structure, then it will actually screen out the dipoles. We started to do that and gave up, and then replaced the metals with the graphene, because it turns out that the graphene will not sort of destroy the device. It will not screen out the dipoles, and actually the dipoles will introduce a big doping in the graphene, which we also like to have. So if we take this stack of three of the Genus layers and sandwich this between graphene electrodes, then we would have a strongly n-doped graphene electrode on one side and strongly p-doped on the other side. So we would have a quite nice diode structure from the built-in dipoles. And yeah, so you see in the band structure how this crossing here, that's actually the band structure of the graphene. And you can see how it's strongly n-doped here on one side and strongly p-doped on the other side. Okay, so this is kind of interesting. Maybe it's difficult to make these stacks. As far as I know, it has not been done so far, but there's still hope. So here you see a device where we are doing calculations on this, just a single layer of this Genus structure, where we have sandwiched it between graphene electrodes. And here there's still a doping of the graphene. It's somewhat smaller than when we have 3 layers of the Janus structure, but it's still there. And what you see here is the IV characteristics, which show that it actually indeed behaves like a atom-thin diode. So in the beginning, you will have tunneling for low bias, and then when the bias gets approximately the band gap of the Janus material, then you have a stronger increase in the voltage. And this material, since it's very thin, we could think that, you know, we could maybe make some kind of solar cell out of this type of materials, since you have this strong dipole. So we also did calculations on this type of device. I will not go more into that, but you could imagine that if you could stack the different Janus structures, maybe of different materials, you could harvest different parts of the solar spectrum with different layers. Okay, so let me switch gears to yet another topic, because what I've been talking about so far is actually without interactions between the electrons. And of course, in devices, the electron-photon coupling is important. And so we did some work on this on the electron-photon coupling in gated graphene. And why we are interested in gated graphene is basically that every device you make, including graphene, since it's a 2D material, you know, you can gate it and vary the Fermi level. So that's always used. So you always include gates in these devices. So we thought about, okay, what happens to the phonon part of the resistivity? And actually, in these very clean devices, maybe with the nicely encapsulated graphene, you will have a phonon limited resistivity. The phonons will always be there, though you cannot turn these off. So still you can have these record high mobilities in graphene of up to say 100,000 centimeters square per volt second at room temperature. Maybe today it's somewhat higher even. But of course you always have the phonons there, so it's limited by this. So this is the resistivity for different dopings of the graphene device as a function of temperature. And you see that there's this interesting crossover from a linear temperature dependence to a more like a T to the 4th temperature dependence. And that's well understood, that crossover temperature here, that's this block Grüneisen temperature, where the available phonon momenta starts to be of the same size of as the Fermi surface in graphene. But if we concentrate on this linear equipartition regime up here of the resistivity, then you can, from the experiment, fit a coefficient, which is basically something we can transform into a deformation potential. So we can estimate the deformation potential or effective electron-phonon coupling from the experiments. And this deformation potential, if we compare to sort of the state-of-the-art DFT calculations and the Boltzmann equation with the relaxation time, then this deformation potential from the experiments is actually maybe a factor of 4 or 5 bigger than what you get from the calculations. So that means that in the calculations, you would get maybe a factor of 4 or 5 higher mobility than what you actually see in the experiments. So we gave this some thought, and we proposed that maybe when you have gated devices, the gate breaks the symmetry. And what is the importance of this symmetry breaking? Well, when you have 2D materials, the out-of-plane modes are actually quite dominating. And this is because the dispersion relation for the out-of-plane modes, that is actually quadratic when you go to low phonon energies. So quadratic dispersion in 2D, that means that the density of states is constant for these vibrational modes. Whereas if you look at the other acoustic branches, the density of states goes to 0. So that means that even at room temperature in graphene, if you look at the ratio of density of states, you have maybe a factor of more than 10 of out-of-plane modes than in-plane modes. So they are in principle very dominating. And also when you look at stacks, for instance, this graphene bilayer, hexagonal boron nitride bilayer, there you also see this flexural phonon. So we have reason to believe that there still could be dominating in a device. But we also know that if we look at the linear coupling between electrons and phonons, then this would be zero from symmetry if we just look at freestanding graphene. So if we move the atoms in one direction and look at the change in Hamiltonian for the electrons, or move it in the other direction, that's the same because we could just flip it around. So from symmetry, these out-of-plane phonons should not matter. Then of course we could go to higher order in the coupling here, but a more maybe simple explanation is that if you break the symmetry by having a gate electrode and a dielectric, then maybe you could induce a coupling to the out-of-plane phonons. So this, what you see here, that's a graphene device, and you have a gate here and different dielectrics in between, so like this. And here you see the Hartree potential of the electrons, and you can see how the gate is breaking the left-right symmetry of the graphene. So we have implemented the calculations of electron-phonon coupling in this quantum ATK software, and then we can calculate, of course, the electron-phonon couplings and all the phonons, and from that we can calculate scattering probabilities between the different electron states in the graphene, and from that we can, if we put it into the Boltzmann equation and the relaxation time approximation, we can calculate mobility. And interestingly enough, if we include this gate, sort of realistic gates, so compared to realistic doping values, you see that actually the mobility is dropping down from something which is maybe a factor of 5 or so above what you see in experiments to down to mobilities which are much closer to what you see in experiments. Of course, this is this may not be the sole effect, but the upshot of this is that, you know, the symmetry in the device should matter. So if you could make it perfectly symmetric, so you have a perfectly symmetric gating of your electrode with symmetric dielectrics around, then that should impact the mobility. Then you could get a much better mobility because you would reduce the coupling to the out-of-plane vibrations. So far, this is just a theoretical proposal, and I've not seen any experiments which really documents this. Probably also because it is somewhat difficult to control the symmetry in the device. Okay, so how am I doing with time, Marco?
You still have, I don't know, so 20 minutes. So if you want to leave 5-10 minutes for questions, so probably have 15 minutes.
Okay, fine. That's much more than I need. Okay, then I will not skip this last topic here. So this is shifting gears again to these organic materials, this nanoporous graphene. So this has been our interest in recent years, and we have collaborated with also with the experimentalists growing these materials. Because there's of course a huge number of variations, because these materials start with a small molecule, a precursor, and then you see you have these bromines here, and once you put this molecule on a metal surface, on the right metal surface, like gold 111, they will actually attach together like Lego and build these structures here. And you can imagine that these precursors, they can be changed quite a lot, because in organic chemistry you can really model this maybe like Lego blocks. So this is, of course, it's not everything which will assemble in a nice way, but there are many possibilities. So of course this is, I think, the first structure, but now the experimentalists have more of these structures in the pipeline. And the nice thing is that they are all bound together by strong covalent bonds. There are also, of course, metal organic frameworks which have been around for years, but here the structures are coupled together with transition metals which make weaker bonds. So it's not so obvious that you can actually stack these or put these into stacks. But this material, they have been able to actually make a transistor out of it, so take it away from the gold surface and put it onto an insulator and a gate. So that's probably also the reason why it broke into science. So in order to simulate these systems, we start with density functional theory again and do a calculation on a smaller unit cell. It could be, of course, bigger than this one, but some smaller structure, let's say maximum 1,000 atoms or something. And then we have ways to take out just the orbitals we need. So we can kind of project it into what you could call a tight binding, but it's a tight binding which actually fits completely with the DFT calculation. So we can make a smaller Hamiltonian out of this building block. And then we have Python code, so we can just in one line basically take this building block and tile it into a large structure. So we can create very easily the Hamiltonian of a large structure of this material. And then we can also apply electrodes to different parts of the structure or complex absorbing potentials, such that the electrons are not feeling periodic boundary conditions or a wall, but they can actually just in a smooth way leave the system. So we have ways to make this into a device. And that means that we can actually take a structure like this and take a part of the structure and treat that with DFT. So we could, for instance, take and put a one-dimensional, like a chip point contact, all calculated with DFT, and inject current from that into, let's say, one of these ribbons here, 1 point. And all this region here is then treated by DFT, and then it's surrounded by tight binding. And then we can see how is the current that we inject from this chip, how is that propagating into this material. And somewhat to our surprise, when we did this, we saw that that it's actually making this kind of interference pattern, the current. So we inject current here from the tip, and then it's sort of spreading out, making this interference pattern. And the interesting thing about it, I think, among others, that's the fact that this interference pattern is something which is well known from optics way back. It's called the Talbot effect. And this is something you see when you have waveguides, optical waveguides, which are coupled relatively weakly. Then you get this kind of Talbot interference pattern. So we are used to know that the electrons in graphene can behave like light. So you can have all kinds of lenses and so on made out of different electrostatics. But it's more surprising that you can actually see this kind of light behavior when you have a structure which is basically built out of molecular structure, of molecular building blocks. But still you have this light, and you can actually fit our interference pattern very well with this coupled mode theory from the Talbot effect. Okay, so now we can, of course, with theory play around, because basically this structure, that's carbon nanoribbons connected by these bridges. But for instance, we could change the bridge, and And the bridge is basically one benzene ring. And the connection is this so-called para connection, where it's kind of symmetric, going up or going below here, when the electron goes above here or below. But we could also connect it in the so-called meta connection. And that means that the path the electron takes in the upper part of the ring or in the lower part of the ring is actually differing. And it's differing by half a wavelength, roughly. So that means you have a quantum interference between these two paths. And that means that this ring here, when you connect a benzene ring in this way, it's really not conducting very well. Sorry. So by changing the bridges, we can change the conduction or the coupling between the ribbons. So if we do the calculation here and compare what happens when we inject into this standard nanoporous graphene, which have been fabricated already, and compare that to the structure where we are now using this meta connection between the bridges, you see now that the electrons are basically just propagating in one ribbon if I inject in one ribbon. So so far the experimentalists are still struggling to make this, and they have succeeded to some extent to do this. It's not as perfect as the other structure, but it's on the way. But of course, in theory, then we can keep dreaming. And one thing we thought about, of course, it's somewhat science fiction. That is, if you could combine these different structures, these different bridges, then you could think that you start with a material which is meta connected, so where the ribbons are not connected electronically very well, and then you could, you could switch to this para connection where they're connected well, and you have this interference pattern, so you have the spreading of the electron waves. And then if you could go back to the meta, you would have what you could call a beam splitter. So you could start to think that you could make some kind of maybe quantum coherent carbon covalent circuitry out of this. Of course, it's a theory dreaming, and once we have phonons there and so on, it might be a different behavior. But this is something we're working on now to look at what phonons are doing in these materials. So with that, I will conclude. And so the basic take-home messages is that in my group we are looking at devices based on these new 2D materials and looking for new operation principles, new design principles. Our main tool is the density functional theory with the non-equilibrium Green's functions, but we have also worked a bit with the Boltzmann equation, but this is in the relaxation time approximation. So we are not really able to do the strong non-equilibrium, which we are in the end really interested in. And then we have also ways to extend this type of calculations, the DFT calculations, to a sort of a multi-scale setting where we can go maybe to hundreds of nanometers. So we go towards the devices. So with that, I will thank you for your attention and take any questions, discussion you might want.
Okay, Mads. Thank you very much. Okay, so questions? Okay, maybe I have some questions. So going to just this last project that you were showing. So if you could just go show again your presentation.
Let's see, I share. Yes.
So what? Yeah. Here. Something that I don't know if I'm wrong. I guess for this you have solved this very big tight binding Hamiltonian.
Yes.
What I don't know. I mean, I don't know if I'm wrong. But what surprises me is that at the interface between para and meta, so there's no reflection at the interface.
Yeah. Yeah, it's basically because the ribbons are the same. It's only the bridges which are changing. So I think that's the reason why you can make it so seamless. There's a bit of reflection. It's not so obvious that we're basically plotting the current here, so there will be some back reflection. But I think you're right that it's not a very dominating effect because it's basically the same ribbon structure.
Oh, okay, that's very nice. Yeah, because I was seeing is like, okay, how about reflect? Okay, so you have, but it's really very minor.
Yeah, I think it's not really dominating, but it's not so clear from this kind of plot because we should really compare the transmission function for the perfect system and then the transmission function for this system, which we're not. We're just showing how will the current run, so the current density.
Yeah, but I guess in principle, if you had reflection, you should be seeing some current going backward.
Yeah. But yeah, I think what you see here is the total current. So there will be some going backwards, but it's not like everything's reflected because it's basically the same ribbon going.
Okay, I see. Okay, and if I understood correctly, so you're not including phonons here?
No.
Okay.
We are trying to do it in some simplified ways. So we have devised some ways to approximate it from molecular dynamics simulations, but it's kind of a frozen phonon type of calculation. So the question is, if we actually did a real calculation like calculating the electron phonon couplings and doing the Boltzmann equation, what you would get, what kind of device properties you would get out of this.
Okay, I see. But I guess that here to get this pattern, you need interference.
Yes. Okay. So that's a different thing. Yes. True. So there So there we have this molecular dynamics kind of way to figure out if it will stay coherent, but that's still in the workings, and I mean there's a lot of stuff there's a lot of approximations going into this for sure.
Okay, but very nice. And just a curiosity, how long does it take to? So how many? So how big is the Hamiltonian here?
Yeah, so I think here it's maybe 500,000 sites or something. 500,000 sites are orbitals, but actually it is actually pretty fast to do because everything is done since it's steady state and we have a fixed energy. We can do everything by a recursion method. Mm-hmm. So it's basically taking roughly one row of atoms or some rows of atom from the bottom and up. So maybe it takes like 5 hours or something, but it's a matter of hours really.
Okay.
But it's also because we only look at one Fermi energy here. So we are only injecting at one energy. So we look at the current just around that energy.
Okay, I see.
Can I ask one question here?
Sure.
So, I mean, from your slide 56. So
56, this one.
Yeah, right. So it seems like, as you mentioned, that it is mostly behaving like a waveguide arrays, and these are weakly coupled to each other.
Yes.
All of this mode. So these are basically flow of electron, right?
Yeah.
because I'm not really that expert on material design. So I will talk about it in the perspective from the light behavior. So these are flow of electron, and it seems like behaving like an optical array where light mode is propagating. And in the second one, it seems like by changing the bonding, meta bonding, so the coupled, the dispersed electron motion is like superposition in a one single, direction. It's not.
Yeah, it's just in one ribbon, basically.
Exactly, I see.
Very little. Yeah.
So it's like that by manipulating the bonding from meta to para. So you are almost like in driving the electron direction, the propagation direction.
Yeah, you can say that. Yeah.
So is it like, you can, the whole in the two-dimensional plane, is it like by changing those bonding, you can actually guide the electron motion the way you want?
And yeah, that's sort of what we would like, of course, in the end, if we could really do a circuitry. But at the moment, the behavior we can control is maybe like a spreading like this, or staying in one ribbon.
So basically what I'm trying to say is, you see, if you like, compare with an waveguide, because waveguide you can bend it, or you have a freedom in the dimensional motion of the electron. But here you are doing it on a 2D surface, controlling the electron motion in a particular direction. So it is as you say, it is a kind of a circuitry, design that you want to control the motion of the electron. So my question is whether you can do it by changing this meta and para bonding on the surface.
I think, sort of, we can do it in this way here. We could also imagine that we do it like we only change on one side to meta, and then it would actually spread to one side. But it will also change the interference pattern here. We have not done that, but what we have done is that we have proposed a way to, without actually having to change the molecular bridge, but maybe just change by removing hydrogen, for instance, or adding oxygen. You could have like a chemical way of switching the current.
I see. So the thing is, like in the second graph, where it seems like you have a very single sharp line. So I think that would be your desired electron motion, that all the electrons are following a particular route without dispersing or without spreading around, and you want to control its motion, so that the maximum electron will be in the same route.
Yeah, that's of course the ideal case if you could control it just in one ribbon. But I think to me, in the first place, what is interesting is that in all these carbon nanoribbons which have been proposed, which are really nice, you can do these very nice, but you cannot really manipulate them into a device.
I see.
When you bond this in a two-dimensional structure, it is something you can actually pick up in a device with these stacking techniques and make into something. I think that's the great perspective of this. But it's still in infancy, and it's also, a very multidisciplinary field, because you need both the chemists, then you need the physicists to make the devices and so on, and to measure on the devices. So it's
interesting. It's interesting. The phenomenon of light kind of dynamics is arising in the electron flow.
Yeah.
Okay, maybe I have just one more question. So actually, I don't have a feeling. So I suppose you could control the interference between the two paths through the nanoribbon with a magnetic field, but probably you need a pretty strong magnetic field to do that.
Yeah.
Probably is
On
not.
the other hand, yeah. On the other hand, the sample is quite big, so I guess you would change the interference pattern somewhat. But that's a good question. Yeah. I mean, this is we have looked at this type of calculation for graphene with magnetic fields and look at this guiding of electron paths, but we have not applied magnetic fields to this type of structure. But that's interesting, I think.
Okay, but yeah, no, I was thinking if you could turn the ribbon that is conducting to a non-conducting one, but most probably you will need a pretty high magnetic field.
Oh, that would probably, yeah.
Yeah, that would
cut it off, that would be
high.
Okay,
now.
So, can you show the equation that you used to simulate this one, the discrete equation? Because in optics, I think I'm a bit familiar with this equation that we simulated for discrete optical array.
For this, yeah.
This one.
Yeah.
So you say this is coupled mode theory.
Yes.
And there is a coefficient Kc. So this is controlling the coupling between the modes.
Exactly.
Yeah, I see.
And actually, yeah. So this Kc actually, this coupling we can. After we've done all the huge calculations and so on, it turns out that this Kc you can kind of extract from the band structure of the small unit cell.
So I'm just curious. So why there is no nonlinear part? So you are assuming it's a linear phenomena, all of it.
Yes. So
I mean, this equation have a nonlinear part. It's called Ablois-Ladic model. Anyway.
So in the optics case.
Yeah. There is a nonlinear part at the end of the second part. There is a plus like psi in a nonlinear fashion. I can show you the equation, but I'm just curious that you are assuming the whole electron dynamics here is a linear case.
Yeah, so it's a one electron theory, so it's Schrödinger's equation, so that's completely linear. But of course, if you look at interaction effects and so on, then you would maybe have some nonlinearity. But
so do you have any solution for this, like any particular?
I
mean, it's the equation, so I'm just wondering if it has any,
that I don't know.
I see. No. Okay, sure. Right. So you call discrete Talbot effect. I see.
Yeah.
Okay, interesting.
But I think it's strange that you make a little bit curious that you make something out which sort of is basically graphene but with holes, but it looks like molecules when you zoom in, and then it behaves like light, like what you expect from light. And I'm not showing the graph, but actually, if you just check this solution here and map it directly on ours, you get pretty much the pattern you expect.
Yes, that's true actually. Yeah. So the Kc, the coefficient. So it's mainly, I think, the coupling coefficient Kc. I mean, at some point you can assume that it's very weak. When the coupling is very weak, what you are expecting here?
Yeah. So that the weak coupling, that's actually this.
Yes, that's what.
That's turning off the.
That's right.
That's exactly this.
Sure.
But I mean, there's huge number of possibilities here. We're still playing around with these structures and trying to invent new structures. Also trying to look at magnetism and spin in these structures. Because once you could imagine that you can actually direct electronic current in just one ribbon, then you could imagine that you have spins in this ribbon localized, and maybe you could manipulate that with the current and so on. So there's many interesting directions here, I think.
Okay. Any more questions? Okay, then I guess we can thank Mas for
Sure, I mean,
very interesting.
it's a very nice presentation and a lot of
Thank you very
interesting
much.
stuff.
Thank you.
Okay. Okay. Now, Mas, if you want to just hang on for, then we can have a chat. I mean, if other people want to say, if you have time, otherwise.
Yeah, sure. I have a meeting in